Thank you very much. It's hard to live up to that introduction. Anyway, I'm going to tell you a little bit about C++. I assume you're not all hardcore C++ programmers. If you are, you're probably at the wrong talk. But I'll tell sort of the background stuff and what I think is fundamental and important. And the general idea is first I go for aims and foundations. I mean, what are we trying to do and how? And then I'll show two case studies because I don't want to give any talk without code. What I do, my work has to do with code and how you write code and how you get it right. So that's what I'm going to talk about. And then I'll go back into design principles, standardization, and the future. And the pictures that I scatter through my talks have something or other to do with C++. So that's the cyclotron at CERN. They use a lot of C++ in that for control, for simulation, for data analysis, and so that's what that one has to do. If you get bored, you can always try and guess about the pictures. And so I'm convinced that you have all used C++ today. And you've probably all used it indirectly and not directly. It's at the bottom of a lot of what we're doing. And there's sort of a sampling of things that has a lot of C++ in it. This is a data group here, right? So we have TensorFlow there. And you can't get me into language wars because I'm never rude about C++ applications like those two. And so it doesn't really matter which language you're using or which hardware you're using. There's C++ in it somewhere. And I'm going to try and make it plausible why that is a fact. It's not that it is a fact, because a fact is a fact, but why, how did it come along? Because it wasn't sort of a big national or international project. It was just some good idea. And my background is distributed computing systems. I started this trying to build a distributed computing system. And to give an example, there is a distributed computing system on wheels. So that's sort of the background. The history of this, basically there was two lines of development that led to C++. The low line here goes from assembler machine code through BCPL and C to C++. This is for people who want to squeeze out the last cycle, the last byte out of their hardware. And this is good, and there's, even to this day, lots and lots and lots of applications that need to do that. But for a distributed system, you don't just have to touch the hardware and use it well. You actually have to get away from the hardware to do any real work. And that started with Fortran here when they figured out that they could actually have a language that was fit for humans as opposed to dealing with a machine. It looked at the application area, which was basically compact linear algebra. And so they built a language with the abstraction built in necessary for doing physics and engineering. And once people got that, everybody wanted one. So the business people got COBOL, et cetera, et cetera. And now we created a lot of communities that couldn't talk to each other. If you were doing computation, you did Fortran, you did not understand about records and record manipulation and storage, because that was COBOL kind of territory. And each language grew around an application area with its abstractions built into the language. This is chaos. So this guy here, that's Christian Nygaard, invented Simula, which was a language that was designed so that you could build your own abstractions. So if you wanted the matrices like the Fortran guys, you could build matrices out of user-defined types. And if you wanted to do data manipulation and record keeping, you could build yourself records like they have in COBOL, and they could live in the same program. That's known as data abstraction. It's known as object-oriented programming. And since him and his friends weren't computer scientists, they were basically not invented in those days, they didn't know about types, so they called them classes. And if you use any language that uses the word class, you can thank Christen there. Oh, by the way, that's Bacchus with Fortran. David Wheeler, one of the 10 people who can claim to have invented the computer, and he wrote the first program on a modern stored program computer. It's my thesis advisor, Dennis Ritchie, and there. And so I took these ideas of low level, high level, merged them into C++, and lots of interesting things happened after that. And so in C++, there's these two parts, equivalent to these two levels of development. You need to deal with the machine model. And so the primitive operations are the operations of the machine. It's not an abstraction of it. If you want to add two integers, you add two integers. You don't look at a type field and do the appropriate addition. It's all compiled down using the machine directly. The machine memory just look like a sequence of objects, and you can point to them using machine addresses. Very simple, very clean. And you can compose higher level things by putting them together. Put a lot of object values of the same type next to each other, and you got an array. Put different things together, you can make a struct. Have things that has a part and another part, usually a sort of control handle and a large value. You got structs or classes. This is really, really simple. This is the key to C and C++'s success, and it is actually an abstraction, because that's not really what computers look like, but this is how you can have a treaty between the compiler writers and the machine architects. So that's a direct map there, and C++ was designed with a principle called zero overhead. I really wanted to maintain the efficiency of this really low-level, simple model. And basically, what you don't use, you don't pay for. So I had noticed that languages have a lot of distributed fat. Things are put into the language because you might like to use it, because most people use something like that. And so you have to pay for it, and it's supposedly good for you. But what if you don't use it? I don't want to pay for it. I'm still thinking about things like network drivers and process schedulers and really high performance stuff. And furthermore, if you use a language feature, you shouldn't be able to hand code it better yourself. Maybe in assembler, but that's getting rarer and rarer. We can quite often beat assembler. If nothing else, we can use compile time computation, so we just load the answer into the machine code. And basically examples of things like points, complex numbers, dates, tuples, things that should be really efficient because you use millions or billions of them. And so you don't want the overhead, no memory overhead, no indirect function calls, no need to use the free store, the heap, the dynamic store, whatever you call it, and you can inline operations very easily. This is the key when you want to use the language, to use the machine well. There's a Raspberry Pi. Anyway, so it's all abstraction. So your Intel machine or AMD machine does not actually execute 86 instructions. It has a layer of silicon that translate the lousy instruction set of 886 into something much better for dynamic and optimization and for execution. So basically, the whole thing is abstraction, and even the hardware is an abstraction. The machine model I showed you for C and C++ is an abstraction, because there wasn't any registers, there wasn't any caches or anything like that, but it creates an interface between the higher and the low level. That's what abstractions do. Yeah, it's abstractions all the way down. And you have to abstract from concrete examples, because if you want to maintain performance and keeping simple things simple and obeying the zero overhead principle, you can't just abstract everything and say, okay, we'll delay all the design decisions till later. That may be what you'll do in a dynamic language or something like that, but then you'll have to pay for it. And this is not C++'s domain. C++'s key domain is sort of a little bit above hardware and a bit below the higher level interfaces. That's where it is on essentially all of the systems today. And so there's a C++ community that we're trying to serve as a standards committee and tool builders and such. That's about 4.5 million according to the surveys. It's really, really hard to count. Somebody found that there was 700,000 C++ programmers in South America. I don't know any of them. Okay? It's hard to count. If you go from your own experience, that doesn't work. And the community seems to be growing by about 100,000 developers each year. People complain that C++ is dying. I haven't noticed. At the latest survey of jobs in languages, Python was number 1, C++ was number 2, and 10% lower was Java. And then, anyway, it's of growth. It's for a language that's been declared dead regularly over the last 40 years, it's not doing badly. It's worldwide and it's in most industries. So at the first approximation, C++ is everywhere on Earth and in a plus places beyond Earth. Let's see. And it's in strange places, like that coffee machine is programmed in C++. I ran into the people that was programming it, that's why it's there. So it's not just big fancy systems, it's also little things, because the machine model of C++ is pretty good for small things. If you're low of power, low of computer and such, it's pretty good at that. So basically, now I'm talking about programming languages, and especially the hard core of applications, and we have to remember what matters. What matters actually is not just all the technical details, it's people. When you build something, it's usually because somebody can benefit from it, and if you do it wrong, somebody can get hurt. And I am quite aware that we have to do things right. So basically, the programming language is part of a system, part of a community where you build things, and there's all kinds of technical aspects here. There's a strong tension between the need of stability and the need of evolution. That is, people say, okay, C++ is too big, too complicated, I want a smaller language that's easier to use and has these 2 extra features. This is not easy to do. We have ways of making progress, but we have to be very careful, because don't break my code is more important than the first things I said. If you can do as many improvements as you like. If you break people's code, they'll get very angry and forget all the good things. So that's fine. And furthermore, one thing that sometimes can be annoying when you read papers and such, people say, this one is the best in the world at this. But that's not enough. You have to be good enough at everything people want to do in the domain, otherwise it's useless. I mean, as they say, no chain is stronger than its weakest link. And if there's something that fundamentally cannot be done in any reasonable way, people will use another tool. This is a tool for some things that it's good at, and not for everything. Definitely not everything. So anyway, I'm going to show you a couple of case studies to get to the code. I'm talking about resource management. That's what we use mostly in expressing the structure of a system. That's what classes, constructors, destructors, copy and move operations. And then I'm going to talk about generic programming, which gives you flexibility, working with algorithms, and that's the templates and concepts. That's the language support for that. And curiously enough, a lot of applications need both of these. This was where the emphasis was back in the previous millennium. A lot of the emphasis here is in this millennium. And here's an example. This is a marine diesel engine. It's a rather large one, about 110,000 horsepower. And to give you the size, I don't think you can see it, but there's an engineer there at cylinder head number 5. The programming that controls that uses these things. generic programming and resource management, and probably not in the most modern form that I'm going to show you, because it was done some years ago. But we know it works, because if a ship driven by one of those doesn't work, if the engine stops, you will read it in your newspaper tomorrow. And I did check the Norwegian liner that ran out of power off the coast of Norway was not with that engine. So it's good. Anyway, both of them has their roots in the earlier C++. They're pervasive today, and they illustrate points that make C++ a bit different, because lots of things every language can do and can do it reasonably well. So I want to emphasize and feature some of the features C++ is good at, and they're used to combine elegance and efficiency. I hate having to choose between elegant and efficient. I mean, there's a lot of people think if it has to be elegant, it must be high level and expensive. If it's efficient, it must be low level and fiddly and full of bugs. I don't want that choice. And I'll show you some examples where you don't have to make that choice. And the fundamental thing is they support the direct representation of ideas in code. So resource management. A resource is something that has to be acquired and eventually have to be given back. Examples are memories, locks, file handles, sockets, thread handles. All of these have to be acquired from something and given back. And systems are littered with them. And so it's worth doing. Furthermore, we don't want to hold a resource for very long, because if you hold resources twice as long, locks, file handles, memory, you need twice as big a computer if you hold the resources twice as long, because your resource consumption depends on how long you hold them and how many you take. And usually you have to take whatever it takes. So we want to do it. Furthermore, we should not have this explicit. That is, you have to acquire a resource, you say, I want it. So you take a book out of the library. And what happens next? You forget to put it back. So we want the release to be implicit, whereas the acquisition is explicit. And we don't want, in other words, we don't want to have it manually managed. We want to just give me the resource and it'll be taken care of. And that's what we do with in C++ using scopes mostly. So here is an example. There's a function, takes a couple of arguments. I want a vector of integers, n of them, and I want to open a file stream on a channel of some sort. Now, that's the name. So this one has to grab memory, n integers somewhere, and this one has to grab a file handler and some buffers to run this, and then we use it. And basically, when you get out of scope there, all of this is given back implicitly, and basically the end of the scope is the first place where you know you don't need it anymore. If that gives you too long resource retention, it's probably because your scope was bigger than you needed it to be. So you have a control there. But basically, memory and file are implicitly released here. And the way this is done is very simple. This came into C++ on sort of the first week in 79 or thereabouts. You have to have a constructor. Here I'm saying I want a vector that is of t. And so it gives me an initializer list of t's that is used to initialize the vector. And the destructor is the one that's going to clean up things, and in particular it's going to release that vector of t's. And here is the lower level abstraction that says somewhere in memory is elements of type t, and there's size of them. So basically here we have the abstraction. There's two levels right here. The user interface and the implementation, and when we use it, we take a vector of doubles with some well-known constants, and we take a vector of strings of some well-known language designers, and basically vector was parameterized with an element type, so basically this generates a type that can be used like that. And again, Here at the bottom of the scope, bottom of the function, the destructor is fired up, and it will release the resources acquired. That's basically it. And this is the backbone of a lot of libraries, including the C++ standard library. You can see here we have vectors, lists, singly linked lists, maps, hash tables, sets, multi-set strings. They are all sort of the handle and the value. They all have constructors that allows you to construct it, initialize them, and they all have destructors that clean up any resources they had in the place. And this goes further. Threads, log guards, input streams, file streams, smart pointers are all done in this way. Basically, shared pointers is what you get in a lot of the languages that are garbage collected. So you can do this to basically have your program work like a garbage collected language. On the other hand, then you run as slow as a garbage collected language, so you sort of minimize those. And basically, you can see the garbage collector is not going to deal with these correctly. That is, releasing a file stream isn't just releasing the memory. If you just take the memory and recycle it, you're in deep trouble because you've just leaked a file handle. How about a thread handler? Leaking a thread handle is a very bad thing because the whole thread with all of its resources are gone and it may still be running. That would not be a good idea. So all of this works recursively. So of course you can have a vector of threads that takes locks and takes file handles and grab memory that has vectors of the whole works. It just works. And it tends to give minimal resource retention. So that was what I was going to say about resource management. Again, the beauty is simplicity of this kind of stuff. And there's just one thing I haven't shown you, which is that when you design a class, you can also say, how do we say how to create it and how to destroy it. But you can also say, how do we make a copy of it, and how do we move it from there to there cheaply. So you can move it between scopes. You don't need pointers to get things out of functions. You just return, if you return a vector, it gets moved out. It means that it's dirt cheap. If you have a vector of 10,000 by 10,000 doubles, it's still maximum 6 word assignments. Usually we can optimize to 3 instead of the 10 million times 8 that would be the answer for copy. Okay, I didn't do that. But anyway, I'm going to switch to generic programming. That is, the point is that we don't just want a vector. We want a vector of something you can specify. It may be that physicists, they used to be able to survive with just vectors of doubles, but these days people want vectors of all kinds of things. So you want to parameterize in saying vector has an element type. And that's how we say it. Ugly syntax, but that was what the users wanted at the time. And now I can say I want a vector of integers. That's t for this one is int. And a vector of string, t for this one is string. Fine and dandy. And as soon as you've done that, which is the first thing everybody wants parameterization for, you want to have algorithms that work on the data structures you just parameterized. So you have to parameterize things like sort. And here I'm switching to something that is that is for C++ 20, and it's sort of it's working with GCC, so it's not science fiction. But I'm not going to use a verbose thing. I'm saying I want to sort something that's sortable, and that's pass a reference to that container. That auto there is a hint to the user that this actually is a template and it's parameterized, and sortable is what's known as a concept that specifies what it means to be sortable. And it happens that you can look up in the manual, in the standard, to see what is sortable. Sortable means you have to be a sequence with a begin and an end. It has to refer to something at random access, and it has to be an element type that has less than. Fine. But it says so in the standard. Compilers don't read standards. You mostly don't read standards, but we can now program it in so that the compiler can see the definition. And I'll show you one later. By the way, one of the things we can do here is say, what if we don't actually want to use less than? What if I wanted to use greater than? And then we use what's called a lambda here in C++. It creates a function object that can compare the elements, and then we sort it with a different thing. So you can parameterize with storage, you can parameterize with element type, and you can parameterize with operations. So it's a fairly general system here, and it's a backbone of data structures and algorithms, and we have to be very, very flexible for this. And the place to look at this is in the STL, that's algorithms, containers, and iterators part of the C++ standard. So we can say find Grail in V. Again, I'm using a C++20 feature, but it's in the library. You can download the library today. It's called the ranges library. So find Grail in V. And this expands to things that is equal to or better than what you can hand code. And we can also say find if find the element in the list that matches this predicate. So again, there's a lambda, which is basically a predicate. It returns a Boolean true or false. So we're looking for something that's less than 42. And again, notice here, this is one type, that's another type. And the algorithms work both for vectors and lists and things like that. So it's very flexible. So that's the backbone. We have containers, we have algorithms, we have concurrency support, which is basically at this level is POSIX or Windows level, but type safe and strongly typed. Those of you who have suffered from void stars and macros, this is the improvements here, and there's some beginnings of novel stuff. We are going towards concurrent algorithms, parallel algorithms, vectorizing algorithms. That'll be in C++. Some of it is in C++ 17, some is in C++ 20. Strings, regular expressions, and numeric types and algorithms. So there's a lot of this stuff. It's not sort of corner case incidental. I mean, those of you who may have thought C++ was sort of C with a little bit extra, this is different. We've come a long way. So generic programming, I started working about this a long time ago. The aims that I articulated in 87, it has to be more flexible than I can imagine. I mean, it's very simple. There's people who build systems that can do everything they want. And I learned very early on that I'm not smart enough for that. The group here can think of things I couldn't possibly dream of. But if I'm a toolsmith, I have to build tools that you can use to build your things, not just the things I like. And it has to be zero overhead, because experience shows that if people have a choice between elegant and efficiency, they very often choose efficiency, especially in the sort of systems world that I work most in. Not everything has to be efficient, but a lot in my world has to be. And I want well-specified interfaces, and, well, I'm finally getting them after 20 years. So basically, I started in 80, and there's a paper from there saying you need generic programming, and we need generic types and functions, and you should use macros, it'll do it. I was wrong. I had the right problem and the rough right solution, which was to parameterize algorithms and data structures. I got the implementation totally wrong. In 88, we got templates. You could parameterize a type or a function with another type or a function. Fine. The only snag here is that it's unconstrained. I can't say what that type's supposed to be. So if I'm doing a vector, obviously the type is supposed to be some kind of element type that you can copy in and out and things like that. If I'm doing a sort, what it should be is a container or a sequence of stuff that you can sort. As I said, the definition of sortable is in the standard. And you couldn't say that. It was a runaway success. People could do all kinds of unbelievably clever stuff with this. And in 16, we got a design for concepts, which is the name of constraints specifying interfaces, so that takes the third part. But this too worked for 20 years and gave us a lot of interesting code for all meetings of interesting. And we can now do better for C++20. And basically the problem was that templates are useful and wildly popular, but they offer compile time duck typing, which is basically the type system like Python, but at compile time. And you could do write-only complex, unmaintainable code, and we had the spectacularly bad error messages, because if you only say that this algorithm or this data type takes a type as a parameter, but it doesn't say what that type is supposed to be. If you have an algorithm that's generic and it takes two different types, there will be a connection between those types, otherwise they wouldn't be in the same function, but you couldn't say that. So you get the messages later. It bothered me a lot. The first thing we did was to introduce functions that can be computed at compile time, because people are using templates to calculate values like 7. People could generate Fibonacci sequences and things like that. And that turned out to be really useful. People are willing to suffer all the problems of this kind of stuff to be able to get the benefits. And they are not stupid people. They wanted really high performance, very flexible stuff, and they got it. So, but anyway, to calculate a value, call a function. So we have functions that can be evaluated at compile time, and we want to precisely specify the interfaces so that we get all the benefits of type safety at the interface level, and that's called concept. It comes in C++20. We have a feature freeze of C++20 late February, so I'm reasonably confident this is going to happen. And anyway, you can use it in GCC today. So it's not science fiction. I love science fiction, but not in technical talks. So basically, you can do this. Template sortable C, sort a container of that type. And I can then take a vector of, of doubles. And it can actually deduce that that is supposed to be a vector of doubles because, well, they're all doubles, so that must be a vector of doubles. I take a list of integers, and there will be a list of integers because they're all integers. You can only do this trick if you have a homogeneous initializer list, but you can do it. And then I can sort the vector and sort the list. Now, the vector is sortable, but the list isn't. The list doesn't have random access. The compiler now knows that, and it will do this, and it'll give the error message, a very simple little error message that says, hey, I need something sortable, and the list isn't. Fine. This is progress through simplification. This is far simpler than the kind of code people have written for the last 20 years and given C++ a bad reputation for being incomprehensible and difficult to write, but superb at performance. I want superb at performance and easy to read. You can sort of complain that this syntax is a bit wonky, a bit verbose, but you can understand it, and we can do better. So here is the solution to it. Okay, I really wanted to sort that list. So how do I do it? Well, we have this function in the standard library. It sorts anything that's sortable, and the definition is there. And so let's make a list that sorts anything that's a list. And a list, we can copy the sequence from a list into a vector. So we'll do that. Then we'll sort it, calling that one. And then we will copy the vector here back into the sequence. Problem solved. This is often the fastest way of sorting a list. Put it into a vector, sort it, and put it back again. And so we can do that. Now we sort the vector, it picks this one, and it sorts the list and picks this one. And the reason for this is very simple. It goes and looks for whether it's sortable. And it finds it's sortable that one, but not with that one. But the list criteria is a subset of the vector criteria. So this is the harder, more interesting thing, so it calls it. For the list, it finds it doesn't match that one, but it matches this one. And again, the subset property is there, so you pick the most appropriate one. So we don't actually say what the relationship by these concepts are. We compute it. So basically, these are predicates. They are compile time predicates. We basically says, is this something that meets that predicate? Is the type of vector something that's sortable? The answer is yes. Is the type of the list something that's sortable? No. Is it something that is a list, meaning we can copy it into a vector and such? The answer is yes. So it just computes that. It works. And the way you specify these concepts, these predicates, just looks like that. We take an arbitrary type, and it's sortable if it is a sequence, if it has random access, and if there is an order for the value type. The value type is a conventional way of referring to the element type of anything. So that's really simple. The hard thing is to do the things that are sort of close to the hardware, deep inside the standard library, and for that we have to write something like this. So be a sequence, T has to meet this criteria. This is a requires clause. It specifies operations you should be able to do on a T. So in a sequence, if it has a member that's an iterator, that's a type, member type, it has to have an iterator, and if it has a begin function that returns an iterator, and if it has an end function that returns an iterator. So basically it has to be able to say this. Here's the beginning, here's the end. That's the first part of being a sequence. And then finally, these iterators has to be input iterators. There's a definition somewhere. That's another concept, another predicate. So you say, is the iterator that comes with T an input iterator? Does it have the operations necessary to be an input iterator? The answer, well, it's maybe, of course, since I don't know what T is. But if you give it a vector or a list, the answer becomes yes. Just computation at compile time, and that's coming. So let me go from the case studies into a little bit about sort of the principles and the ideas behind this. And there's people who say, just go, show me the syntax. Don't give me this philosophy stuff. I know how to program. I don't need to be taught. There's a lot of people with that attitude. I think it's wrong. Without philosophy, the language design becomes hacking. You just hack in anything that looks good, and next year you'll decide you made a mistake and you have to back out of it again. And when you build a language, you don't get many chances. Once you have users, you have acquired an obligation to support those users and not break their code. So you have to have principles to work along. Yes?
I'm trying to learn C++, and I actually bought your book, The Design and Evolution of C++.
Yeah.
Just hoping that that was going to help me understand your language more, was understanding the philosophy of it.
It will.
And especially being a philosophy major at this school.
Okay.
Super freaking helpful.
I spent 2 years studying philosophy. But anyway, you will not be soft. It's not Kant. It can be read. And first of all, read the first half. That's the one that has all the good stuff in it. And I'll actually give you some quote on some of the next slides. Anyway, so basically you have to have principles. They must be articulated, because if you don't say it, how can people understand it? If you just give people the examples, they will find a rationale for why that example is right. And quite often they'll be totally wrong. And so they will, the next time they look at an example, they'll make the wrong deductions. And basically, language really is more than a collection of features. It's a sort of a fine mesh set of features of interrelationships between them. And don't solve a particular problem. There's languages that do that, but that's not my business. I'm trying to do general purpose, so you solve general problems, you give people tools to solve their own problems. Don't add fashionable cool features. Fashions come, fashions go, and I try not to follow them. That means I'm a little bit slow on picking up on new stuff, but most stuff doesn't stay new and interesting, so it's good to be a little bit slow. And we have both stability and evolution. Don't break the billion lines of code. I have had discussions over the last month if this statement is misleading. We know there's hundreds of billions of lines of code there. The real question is, could I say trillion? Have we beaten the 1,000 billion lines of code? There's people that says yes, but as I said, I have to be conservative, so I'm not sure. We have to evolve we don't break those, we have to evolve because the world is evolving, and we can't outpace the community. This is actually a real hard problem because what is the rate of change you can impose on a large community? And people saying sometimes that I'm crazy and want to move too fast, and they sort of put the brakes on, and I get very frustrated. On the other hand, there's a lot of people that says we're not moving fast enough. So if everybody is unhappy, it's probably a good compromise. And you can't always get what you want. So just because I want it doesn't mean I can get it. So you have to listen, you have to learn from the community and things like that. Oh, that's an engineer, right? Sorry. And there is, if you want to see more of it, you can see the Design and Evolution book, which was the one you pointed to. It is by far the most fun book to write of all of mine. So here's some examples. First rule of the game is that C++ is a practical tool. It is not an academic project. It's not trying to be the most beautiful language ever. There's a quote by me from about '84. It says, even I know how to create a prettier language. But that's not the purpose of the exercise. It must be driven by real problems. Theory is great once you know what you want to do. It is not a good guide to what you should want. We will not reach perfection. We have to be useful now because we've got users. We can't say, okay guys, I can build a much better language. Just wait 5 years and I'll solve your problems. People can't wait for 5 years. Their mortgage will not be paid. Their companies will be ruined and things. So it has to be useful now. This one is hard. It was true at the time I wrote it. It's really, really hard to make sure that implementations are simple. Hardware is getting weirder, and people's uses of it are getting more advanced. Always provide a transition path. If you have an old feature and a new feature, you have to have a way of getting from it. You can't just break all the old stuff. You have to be able to evolve. You have to gradually adopt things, otherwise it doesn't work. It's a language, not a complete system. There's people that has built languages that came with an emailer. No, C++ doesn't come with an emailer. It comes with a facility for building an emailer, and probably your emailer was written in C++. And you can have that as a library and call it from it. It's not in the language. Provide comprehensive support. If you do something well. It is more important to enable good programming and to prevent errors. That one is really, really difficult to get people across and says, but you could break my computer. Yeah, sure. Don't do that. It hurts. That is, it is important to be able to solve problems, and it's also important to be able to avoid bugs, but it's not the same thing. You can do a static analysis, you can do a dynamic analysis, you can do runtime checking to stop these errors from happening. We're getting better and better at that. But fundamentally, this goes back from the early design days. We want to be able that you can express your ideas. And don't try and force people. Programmers are clever. If you try and say you must do exactly this, they'll do the opposite. So don't try that. And there's explanations in D&E. There's also some language technical rules. Notice that none of these rules have anything to do with programming language construct as such. This is the background philosophy. Then I like the static type system. That is what can tell me that my program is free of certain kinds of errors before it starts to run. It's the kind of thing that says you can optimize so you can get good benefits. It's nice to have a language that's dynamic and it puts you in the debugger if you make a mistake. This is good for development. It's good for getting things done. But if your program is running on say the telephone switch in Bogota and it gets an error late Sunday night when it's raining, there's going to be no programmer there. And even if there was a programmer there, the likelihood of knowing this C++ program so that you could use the debugger is about 0. So for the kind of domain I'm working at, static type checking, static analysis is very important. Provide good support for user-defined types and built-in types. A lot of languages say if you have, say, a user-defined type complex number in some languages, there's different scope rules, different allocation rules, different initialization rules than from an integer. So how do I move from integer to complex arithmetic? How do I write a piece of generic code that can use both? The answer is I can't. So I want exactly the same rules for user-defined types as for built-in types. So I can build an infinite precision integer. And it will, from the point of view of the user, be exactly like an integer. It has the same operations, it has the same scope rules and all of that. That's an early one, and we're almost there. You can now use this at compile time too, user-defined types. I like locality, I don't like orders, anyway. And then the zero overhead principle. This is a lot, you can find it. So here's an example. Principles have consequences. And so I have been talking about the zero overhead abstraction. I've talked about type safety. It follows that if I can write the answer directly instead of computing it, I've violated the zero overhead principle in some sense. So I should be able to compute that thing at compile time so that I don't have to go over on the doodle pad and do the calculation. Furthermore, I should be able to do that with things that has type safety, which requires user-defined types. So I have to be able to compute with user-defined types at compile time. It follows. It took me some time to realize that, but it did. So we had requests. There were some people doing embedded systems in Japan that wanted an integer square root. They want it calculated at compile time. So we can do one. And by the way, there's a very old feature, auto. It says that the type of x is the type of its initializer. So I can do I square root of that. It can be in the code. You can see what it is. You can see what it means. You don't have a magic constant. And you can't get it wrong on the doodle pad. And you can't do it on the doodle pad, move it into the code, move the code to a different machine with, say, different integer sizes and get a different result. No. But this one is more interesting. It says, give me the weekday of June the 21st, 2016. That's obviously a user-defined type. And as a matter of fact, it's a user-defined type with a rather interesting initializer. A friend of mine, Howard Hinnant, has built this library. It's going to be in C++20. It's been in production use for a few years. So you can do that, and you get the weekday, and that's fine. And you can actually do that at compile time too. I haven't shown it this, but I could put a const expr in front of here, which would force computation at compile time. As it is here, the compiler is free to do it at runtime or at compile time, and it will pick compile time. But that's not guaranteed. You can guarantee it too. So, and you can compute optimal types too. That's where you get into metaprogramming. You generate your types at compile time. So you can say, here's a variant. If it's small, put it on the stack. It's local. Otherwise, put it on the heap. That's pretty ugly stuff there. You can get used to it. I don't think you should have to get used to it, but that's the way it is. But I can use it easily. Variant of int, variable of int, it'll live on the stack or on the static store if that is. And variables of humongous, you initialize with something big, it then puts it on the heap. That you can do. Very simple example of template metaprogramming. And so C++ is being used by lots of people. So we have a standards organization. I think it's a necessary evil. I thought it was essential. People told me it was essential. People from IBM and Sun and HP said, you really want to do this standardization? I said, no, we're not ready. I said, ow, ow, ow. So I agreed to do it. And there's many kinds of standards. We chose the gold standard, which is ISO. Long-term stability is a feature. We can't mess around with the language. We can't twist it for the benefit of some organization. Inventor neutrality is important, and of course you have major dangers, design by committees, stagnation, and things like that. And here you see the problem. That's what it looked like in the really old days before color came into the world. So it grew, grew, and it is bigger now. 180 people. There's not 180 people in this room. We work by consensus. How do you get a group like this to agree on anything? Especially if the things affect them in their everyday work and their friends and their companies. It's hard. So this is really hard. So there's also a lot of energy, a lot of enthusiasm. How on earth do you get this to actually work out? And so far so good. We have the evolution. The workhorse is the old 98 standard. Then we got 11, which was a major growth, and basically created the framework for the language we've got today. We decided that this was far too long between standards, so we went much faster. And here, 20 should become great. We will get concepts, modules, code, change ranges, things that I've shown you some of it today. And we have a feature freeze, and we have delivered on time twice. So there's a good chance that this is going to be true. Of course, the language is not perfect. There's people who think that today we have everything that could be done. Evolution has ended. Science is at the end, all of this. I don't believe it. We can do much better, and we must do much better. There's hardware changing. We need to simplify the use, and we're continuously doing that. We have to maintain stability, and there's a huge education process that's necessary, and we have to improve the library and language and such. This is fine. This, by the way, is Hercules, the original Greek hero. He is trying to kill the Hydra. The Hydra is a monster with the interesting property that each time you chop off the head, 2 new ones grow out. And that's what it feels like doing a general purpose programming language. That is, whenever you actually solve a problem, you just get more users and they get harder problems. You can't just do things through language design. You actually have to teach the community how to use it. And there's an interesting project here that goes for the Holy Grail, which is this. I want to write, and you can write C++ today, that has no leaks, it's type and resource safe, no leaks, no memory corruption, no garbage collector. It violates the zero overhead principle. No limitation of expressibility. It's easy to be safe. You just stop doing anything of interest, right? It's being safe while doing really interesting things that matters. I don't want to have slowness. This is C++. I don't want to design a new language. It's just too hard work. And I want it tool enforced. We're only partially there. I can guarantee most of those with a standard static analyzer today. This is not science fiction. On the other hand, it is not deployed at scale. This is why I said work in progress. You can go and find it on GitHub. I'll make the slides available. And basically, so I have a conjecture here that I'll end with. And this is a conjecture I've been sort of creeping up on for years, and I would like to prove. The most direct expression of an idea is the simplest, safe, fast, composable, and the easiest to maintain. And to give you an example of this, when I have been doing optimization over the last couple of years, my first bit of the optimization is to rip out all the clever stuff. and then see if it's necessary. And then, having gotten the simplest and direct version of the program, I can then put in clever stuff if I need it. But quite often I don't need it. The compilers, when given good, simple stuff, are superb. Give them complicated stuff that I can't understand, they'll probably generate bad code, because they can't understand it either, the optimizers. So we're getting close for that. And we aim for that, and then to keep simple things simple. That is the way you can have a language that grows and gets bigger, but is simpler to use. You can't make a language smaller when it's in wide use, because that breaks people's code, right? But you can provide a layer that's simpler to use. So the classical example is we have a range 4, or an algorithm. It just says do this to every element in that thing. You go down one level, and you have the C style of loop with a loop variable and such, and people might do nasty things to the loop variable, but sometimes you need to do nasty things to it, so it's more complicated. And then finally you can go down, use continues, go-tos, breaks, and all of that, another level. So basically the design becomes a sequence of layers. And the reason I call it the onion principle is, by and large, each layer you take off, you cry more. You get more opportunities for bugs, you get more code to look at and things like that. So we can simplify things while making it bigger. The language doesn't get simpler, but its use does. And that's what I'm trying to do. And I hope we have time for some questions, even though I'm a bit over. Sorry.